This app blocks debuggers from being attached, it exits early if you try to inject any code, it even finds a way to crash your entire phone if you run it with a jailbreak on. Like who even does that? The sorts of things we do on this channel, like modding TikTok to only show cat videos or fixing crashes in other people's apps, all require the ability to take an app and poke at it to see how it works. But it's not uncommon for iOS apps to include additional protections to keep prying eyes away, like jailbreak detection or code obfuscation. Though this app has a surprising combination of them, why does a widget app need this much protection anyways? Well, that turns out to be a whole separate thing that requires its own video. So remember to subscribe if you want to catch that one next. But for today, let's focus on how to even get past these protections in the first place. I want to start with getting the debugger attached because that might help us with the other two. So we're running this on a jailbroken phone, which means usually we can just SSH into the phone itself and then start a debug server attached to whatever app we want. And then we should be able to interact with the app however we want, print debug information, figure out what's being passed to different methods, all that good stuff. Like our good old friend recursive description to print out information about everything currently on the screen. That's how it should work. But if I try to do the same thing to this widget app, we get a segmentation fault, the debugger doesn't actually attach, and now the whole phone soft reboots because of one of the other protections. We'll get to that. First, this failure to attach the debugger is thanks to a function called ptrace. Now this is a private API on iOS, meaning you're not supposed to call it, but it is a public API on macOS, which means we can actually pull up the documentation for it. Now, ptrace is super cool. It is the thing that powers most of the debugging functionality that we know and love. But in particular, we're interested in this operation, pt deny attach. It will prevent any future debugging requests, and if the app is already being debugged, it will exit out of it entirely. Now, there are effectively two ways an iOS app can include this functionality, and how we tackle it depends on which way it's using. The simplest way is to just call the ptrace function like you'd expect. And this is easiest to show in a macOS app where, again, it's actually a public API. So if we take this sample app, which is literally just the default console template from Xcode. If I run this, Xcode will build it, attach a debugger, and then we'll see this hello world message printed out at the bottom. But if I import the ptrace header, and then I call ptrace with pt deny attach, and then there are 3 more required parameters, but none of them are actually used in the case of deny attach. If I rerun with just this function call added, we'll see instead that the program exits with an error code, and we don't see hello world printed out. It saw that Xcode attached a debugger and exited early. Only if we have a debugger attached though. If I go here and tell Xcode to not debug the executable, and then rerun, then everything works fine. We get our hello world again. The function call is very similar on iOS, but again, because it's a private API, you have to go through the normal song and dance of finding a reference to the library that declares the function and then finding a pointer to the function at runtime, which we've seen before, but the function call itself is the same, and conceptually everything works similarly to the Mac version, where if we try to run this, Xcode will launch the app, but because it tries to attach a debugger, the app exits immediately. So that's how pt deny attach works. Now, how do we work around it? Well, there's one easy weakness to this function, which is that it only blocks the debugger after it's been called. So if I put a breakpoint anywhere before that call and then rerun, we'll see that the debugger attaches just fine. And this gives us a lot of control to actually circumvent that ptrace call later. There's a bunch of ways we could do that, but probably the easiest is to just set a breakpoint on ptrace itself. And then when we continue execution, we can see the app is calling ptrace, and we can instead just say, no, you're not, and use thread return to back out to where we were before the call without actually invoking the function. And now we can resume execution, and we've successfully skipped the call, the app is launched, our debugger is attached. Cool, so now let's go try this in our widget app. I'm gonna launch a debug server again, but this time I'm not gonna point it to any currently running process. Instead, over on my own machine, I'm gonna start LLDB. I'm gonna tell it we're connecting to a remote iOS device. We will connect to that device, and then I'm gonna use process attach to tell it which process to connect to. I'm gonna pass in top widget as the process name, but I'm gonna use the wait for flag, meaning this process doesn't exist yet, but we want to attach to it as soon as it launches. And now if we rebring up the home screen and try to launch the widgets, we see LLDB spring to life, and now it's successfully attached to the app before any of its code is executed, including the code that tries to kick out the debugger. So now we can set a breakpoint on ptrace. It's going to give us a warning saying that it couldn't find it yet, but that may be fine. The app may be pulling in the framework sometime after launch like we were doing here. So I'm just going to go ahead and continue execution, and we can see that it does indeed find that ptrace function and it adds it to our breakpoint, but that breakpoint is never triggered. Instead, we are kicked out of the app just like before. And then again, separately, the whole thing soft reboots the phone just for fun. So I mentioned there are 2 ways to integrate this functionality, and this way actually has some downsides. 1, it's super easy to find and skip this ptrace call, just like we saw in the simulator. And 2, you have to do all this suspicious looking runtime lookup stuff that makes it very clear that you're using a private API, which you don't want to do when going through app review. So we can actually feed 2 birds with one stone here and skip this ptrace function call altogether. See, if I rerun this and we step back into that ptrace function, we can see that the actual implementation is surprisingly short. There's some error handling at the top and bottom, but the critical part is this one SVC instruction here. That's a system call, meaning this function is delegating to the kernel to do the actual heavy lifting, which makes sense for something as low level as a debugging integration. So what some developers will do, instead of calling this ptrace function, is to just make this same system call themselves using essentially the same assembly. By the way, you generally should not write inline assembly in this way, but it makes the explanation easier. So if you're not well versed in assembly, don't worry, this one's actually easier than it looks. We have the same 4 parameters that we're passing in our original ptrace function call. There's pt_deny_attach, which is literally just the integer value 31. Followed by 3 zeros. And we're passing these all in registers x0 through x3. Now we need to tell the kernel which system call we actually want to make. iOS expects that to be passed along in register x16, and in this case, we're just passing the value 26. That's the value corresponding to ptrace, which we can actually see in the disassembled version of the real ptrace function. We set register x16 to hex 1a, which is 26 in decimal. So this tells the kernel what system call we want to make, and then we actually make the system call itself. The hex 80 here doesn't really do anything. We're just required to pass a value, and iOS uses that value by convention. But that's the entire assembly. So if we rerun, we'll see the same thing as before. We will start the app and then immediately exit, all without ever calling that private ptrace function. Now don't get me wrong, this is also not allowed by Apple. It is not valid to call a private API by just replicating the assembly of it yourself. But it is a little harder for them to detect and a little harder for us to work around. There's now no common function like ptrace that we could set a breakpoint on to detect and skip. We instead have to figure out where in the binary this system call happens and then decide from there how we want to bypass it. So to do that, we need to open a decrypted copy of the app in a disassembler and then figure out where in these millions of instructions that system call lies. System calls can be kind of common in a normal app disassembly, so just looking through all of them is probably not going to help us a ton. Luckily, if we look back at those instructions, one of them sticks out like a sore thumb, which is setting register x16 to the value 26. That's a very specific value being set to a very specific register. I wouldn't expect this to appear in app code very frequently, so looking for this instruction might be a good way to narrow our search space down. Now, most disassemblers should give you an option to search through kind of this raw text disassembled output, but that can be pretty slow. Like, you know it's bad when the search pop-up even warns you not to do it. Plus, it can be tripped up by small formatting differences, like whether numbers are displayed in hexadecimal or decimal. So it's an option, but we might have a better one, which is to find the exact bytes corresponding to this instruction and then search for those. I like armconverter.com for this. It's a really easy way to paste in an assembly instruction and get the corresponding bytes out. So hopefully these bytes appear somewhere in the binary. We should also note that there was another way that you could write this instruction, which is to use W16 instead of X16. That's the same register. One's just a 32-bit view and one's a 64-bit view. So we should look for both. So we can search for exactly those bytes in the disassembler, and it looks like for X16 we found nothing. Let's try for W16. And this time we end up seeing 4 instructions throughout the whole app. That's a lot more manageable. So if we look through these, this first one doesn't look too suspicious to me, meaning the assembly doesn't look like the assembly that we expect from our Xcode example. The second one also doesn't look too suspicious. The third one looks very suspicious. That is practically the exact same assembly we have in Xcode here. We're setting register X0 to hex 1F, that's 31 in decimal. Setting the next 3 to 0. We set register W16 or X16 to 1A, that's 26. And we make our system call. So perfect, this is the part of the app that is preventing us from attaching our debugger. And turns out the fourth occurrence is just a different branch in this same function further down. So it's very clear where we need to patch out. So what I'm going to do is attach a debugger to this widget app again with the exact same setup as before, where we just tell it to wait for the widget app to be launched and then it comes alive as soon as we do. And this time I want to set a breakpoint on the addresses where this system call is being made. And I can do that using breakpoint set -a for address. And I'm going to come over here and scroll over to see the address of this instruction. And we can just paste that in here. Now this alone isn't sufficient because our disassembler doesn't know anything about where this binary is actually loaded into memory. But LLDB can handle that for us using -s, meaning treat this address as relative to that particular binary. And now I'm going to create that breakpoint, and then I'm going to do the same for the other system call down below, where I'm literally just going to swap out this address and submit. And now hopefully just a moment or two later, our breakpoint is hit and we can actually see the exact same instructions as we have in this first occurrence of the system call right up here. So now we're paused right before the system call. What I'm going to do is take the address of the instruction right after it, and I'm going to use the jump command to just skip to that address. You can see in our previous output, there's an arrow on the left-hand side saying we're about to execute the SVC instruction. Now that we've jumped forward, if I run the disassemble command and scroll up, you can see that that arrow says we're now right after that system call. And so now if I continue execution, we're in. Right up until that happens and we hit the second protection and do the soft reboot. But you'll notice something very cool here. LLDB is actually still attached. By fixing the debugger, we now have the ability to get some insights into the whole soft reboot thing. I said at the start of this video that the app was doing the reboot thing on purpose. Now let me prove it. We can see here in the debugger that the process was sent a kill signal. If we run BT to see the current stack trace, we can see what it was doing when it was killed. And specifically, it's running a function to capture the screen contents, which is Interesting. We can also find the last address where we are going through our own app code right here. Now, the first thing we'll want to do is look at this function in a disassembler. But again, there's a disconnect here where this is the address relative to wherever this process was loaded into memory, which our disassembler knows nothing about. But we can use image lookup -a for address and paste in that address. And that output will include the address in the binary itself. So we can take this address and jump there in our disassembler, and we can immediately see some references to capturing the current screen content, so we know we're in the right place. If I bring up the decompilation of this function, we can see that we have an infinite loop with no way to break out of it. And in that infinite loop, we call UI screen main screen, and then on that we call snapshot view after screen updates. This is a public API and a fairly common one. It just creates a snapshot of a view. But it's the surrounding implementation that's so interesting here. This is a very memory intensive method, but we don't do anything with the result. We're just taking snapshots in an infinite loop. Sometimes the decompilation can get things wrong, but if we look at the graph view of this function, we see the exact same thing. There's an infinite loop as shown by this one arrow here, and all we do within that loop is snapshot view after updates. The result is never referenced, there's no other methods called, we have no way to break out of the loop. And again, I need to emphasize how crazy this is. Using too much memory can of course get your app killed, but it seems like somebody found a method that if you call it too quickly will soft reboot the whole phone. And then they chose to take that information and write a function to call it in an infinite loop and just torpedo the phone of whoever's running this code. Like, that's just delightful. Let's see if we can figure out why this is being called. In LLDB, this was the only line of the stack trace that was from the app itself. The line before that is just from the combine framework. But in the disassembler, we might be able to learn more. So I'm going to go to the very start of this function and I'm going to look up all the places that reference it. This can be places that call the function directly or places that pass this function address as a callback, which is most likely if we're seeing it invoked by the combine framework. And looking at this first reference, if we bring up the decompilation, we can see that we call ns-notification-center.publisher, and then we're subscribing to updates from that publisher. Back in the disassembly, if we scroll up a little bit more, we can actually find the name for that notification. It's com.apple.tw.twrr. TW is probably top widgets here, the name of the app. I don't know what RR means yet, but we can interpret this as us subscribing to notifications named com.apple.tw.twrr, and whenever we see that notification come in, we enter that function to take an infinite loop of view snapshots and torpedo the phone. So now the question is, where's this notification fired? And if we double click into it, we should be able to see all the places within the binary that reference this string. This first one is where we just were. The second one doesn't look too interesting. The third one does look to be a place where this notification is actually fired based on this post notification name call. And if we zoom out and try to figure out what conditions we're actually firing this in, we can see that it's based on a check for an NS user defaults value called tw.risk.checksum. Maybe risk is what one of those R's stood for. The RR could be risk result. But either way, I think it's clear at this point what's happening. The app is doing some sort of risk check on our phone. We do not pass the check, and then it decides to crash the phone as a result. We could keep following this chain up, or we could try to find other ways to poke around at it. Like, there's a lot of functions in this app that have jailbreak in the name that are obvious places to start. But we don't actually need to, because we know where the final result of this whole check is handled. It's in that infinite loop function. And that's enough. If I start an LLDB session again, and just like before, I'm going to set a breakpoint on that ptrace system call, but I'm also going to set a second breakpoint at the start of this function. I'm just going to take this address here and set it the same way we did for our last one. Now I'm going to continue execution. We should hit breakpoint 1 first. That is the system call for ptrace. I'm going to go ahead and jump forward again to skip it. But this time we hit breakpoint 2 as well. That is the start of the infinite loop function, meaning the app has decided that it should torpedo our phone. And just like before, I'm going to use thread return to skip the execution of that method entirely. And then we can hit continue. And there we go. We are properly into the app. We can pause execution. We can do all our normal things to poke around in the app, set breakpoints on method calls, whatever we want. Phew. Again, I cannot stress enough how weird it is for an app to try to take down your phone just for debugging it. I think that's hilarious. Now, I mentioned one more issue at the start of all this, which is that when we try to inject new code into this app, it also crashes. I'll often do that when I have a debugger attached when I need some more complex utils to help me dive into an app. Like if I quickly want to log the accessibility information of all the buttons on screen or something. You could do that just from LLDB, but it would be very painful. It's easier to just write that in a framework and then inject it into the app. But you might also want to do that if you don't have a jailbroken phone at all. You can inject tools like Frida or Flex to get some initial exploration of an app without actually needing a jailbreak. Say if we want to take this app and inject Flex into it. So here's our new copy of the app with Flex injected, and if we try to launch it, immediate crash. In fact, it crashes so quickly that it doesn't quite reach full screen yet. So is this one more protection, checking what frameworks are loaded at runtime and crashing if anything unexpected appears? Luckily, no. Some apps do that, but we have a much simpler explanation here. Let's look at what method's actually crashing. We could do that super easily with LLDB, same as before, attach to the app and then see what the stack trace is when we crash. But if you were injecting code into this app because you didn't have a jailbreak, meaning you don't have LLDB either, then we can get the same information looking at a crash log from the device. You could pull this from Xcode, or if your phone's too old, which this one is, you can get a item from library logs crash report or mobile device. And here we can see a recent crash from the top widget process. So I'm gonna go ahead and open this in Sublime. So we can see a couple things here. We can see that there was an exception of type exe breakpoint. We can see that it was thread 0 that caused that exception. And here we can see the actual stack trace of that crash. So the very top of the stack was this relative address within image index 1. And if we look after all this thread information, we should be able to confirm that index 0 is DYLD, index 1 is our actual top widget app. So that means we have the relative address within the top widget binary that was causing the crash. I'm gonna go ahead and convert that to a hexadecimal number. And then back in our disassembler, we should be able to look up that address. And we can see that it corresponds to a break instruction. So this lines up with what we saw with the exe breakpoint exception type. And this is the instruction we'd expect if the app's code intentionally wanted us to crash here. Now, if we go to the decompilation of this function, we should be able to pretty quickly see what the issue is. And it's this called the container URL for security application group identifier. This is a public, perfectly normal method that returns a folder that multiple apps or extensions in a single group can access together. Usually apps are completely sandboxed from each other. They basically have their own little mini file systems that they can write to, but putting them in a shared group means that they can access shared resources. The problem is that groups are defined as part of the code signing process, and we just threw away the existing signature by injecting code and re-signing the app, meaning we threw away whatever groups the app was already a part of. So when we call a function like this that is passing a group identifier, it's going to pass something like group.topWidgets, which after re-signing, this app is no longer part of. So this method, which is supposed to return a URL pointing to the local file system, is probably returning nil, and maybe we are force unwrapping that and crashing the whole app as a result. So this is actually a pretty common problem, and even though it's acting like a defense here, it's probably not on purpose. This is a widget app, and it makes sense that it would need to be in a group with its widget app extension that actually handles displaying widgets on the home screen. By far, the easiest way to work around this kind of issue is to not re-sign the app. A jailbroken phone makes this significantly easier. You can inject frameworks into an app using a jailbreak tweak without ever having to re-sign it, or you can even run code that has invalid signatures. You can add whatever apps to whatever groups you want. Jailbreaking makes a lot of code sign issues just go away. So that's what I did when I was looking into this app the first time. I created a jailbreak tweak that injected the utilities I wanted, and then I was able to reference those from the debugger instead. In a pinch though, if you were injecting a debugging framework because you don't have a jailbroken device, you can still sometimes work around things like this even while re-signing the app. The app is crashing because it's expecting a URL to be returned here and it's not getting one back. What we can do is create a framework that swizzles that method to make sure that a URL is always returned. In this case, we're setting it up so that anytime that container URL for security application group identifier method is called, God, that's a mouthful, we are instead going to call our replacement method down here, which just returns some temporary directory. It's worth noting, this is not an equivalent replacement for what the app is actually trying to do. This method is being called because the app wants a shared folder that both it and its app extensions can access, and we're lying to it and saying, here you go, here's your shared folder, even though that is definitely not a shared folder. But depending on what you're trying to do, that might actually be fine. I've actually found little patches like this will often break the app extensions themselves, but I usually don't care about them, and the app still works fine, especially if my goal is to just poke around at how the app does something and I just need the basic functionality to work. You can maybe do something more advanced here, like create your own app group and replace the identifier being passed to this method, and do that in all the app extensions and any other place that's referencing these group IDs. Either way, if we build this framework, and now we add it to the list of frameworks that we're injecting into the app, now we have the new version of the app installed and we need to bypass all the existing protections again. So one more time, we'll go ahead and launch, set our 2 breakpoints, continue execution, jump forward, thread return, and there we go. We are properly in the app, this time with Flex injected, so we have all these awesome debugging tools. That being said, some parts of the app are broken thanks to the re-signing process. So we could go figure out where those are, but at some point, just injecting code using a jailbreak so you don't have to re-sign probably is worth your while. Either way, we are now in the app, we have a debugger attached, we can inject code, and we have bypassed the jailbreak detection. What were we here for again? Oh yeah, that's for next time. Until then, thanks so much for watching. If you find and bypass any of these protections, or add them to your own app because you just learned about them for the first time, please let me know. This is my second time recording this because I forgot to record my screen the first time, so I'm gonna go get some food. Thank you so much for watching. I will see you next time.